Chapter 6, Precise Synchronization. First, background. A cooperative process is one that can affect or be affected by other processes executing in the system. Cooperating processes can either directly share a logical address space, that is both code and data, or be allowed to share data only through files or messages. Concurrent assigns to shared data may result in data inconsistency. However, in this chapter, we discuss various mechanisms to ensure the orderly execution of cooperating processes that share a logical address space, so that data consistency is maintained. Okay, first, suppose that we modify the producer-consumer code by adding a variable counter initialized to 0 and incremented each time a new item is added to the buffer, and is decremented one item is removed from the buffer. Okay, so bounded buffer problem, we already know. We also called it producer-consumer problem. So here is the shared data by producer and the consumer. We can see this is constant. Buffer size equals to 10, and this is a structure. This is a structure, okay, that represents an item put in the buffer, and this is the buffer. It is an array, the buffer, and this is in pointer, represent the location, that is the location for the producer to put an item into the buffer, and this is out, represent the location for consumer to retrieve an item from the buffer, and this is counter. All these are shared by producer and the consumer. So now this is the producer process. This next produced is the local data of the producer process, and it is used to put the atom that is that is produced by the producer and will be put into the buffer. Okay, so we can see here when counter equals to buffer size, that means there is no place for producer to put an item into the buffer. So the producer will do nothing, just check, just loop and loop again, checking the condition till its time slice elapse. Okay, till its time slice elapse. Okay, and if this condition doesn't satisfy, then the producer will put an item into the buffer and move the counter to the next position, next empty position, and the buffer is incremented by 1, means there is one more item in the buffer. Okay, the counter incremented by 1. This is producer process, and this is consumer process. Also, the local data is next consumed, that is put the item retrieved from the buffer by the consumer. Okay, also the condition is if the counter equals to 0, that means there is no item in the buffer is empty, so the consumer has to wait. It will do nothing, just loop and loop again, checking this condition. Okay, If this condition doesn't satisfy, then that means there is an item that the consumer can retrieve. So the consumer will retrieve an item from the buffer, put its in local variable next consumed, and move the out pointer to the next position for the consumed to the next full position. Okay, then decremented the counter by 1 to represent there is one more to represent for the 4 items there is decremented by 1. It is decremented by 1. Okay, so we can see the statement counter plus plus and the counter minus minus must be performed atomically. Although the producer and the consumer routines shown above are correct separately, they may not function correctly when executed concurrently. As an illustration, suppose that the value of the variable counter is currently 5, and that the producer and the consumer processes concurrently execute the statements counter plus plus and counter minus minus. Following the execution of these 2 statements, we can see that we can show that the value of counter may be incorrect as follows. Know that the statement counter plus plus may be implemented in machine language is because in producer process this statement counter plus plus is a high level language statement, so it must be compiled into machine level instruction, and so we suppose that may be implemented in machine language as this one. Register 1 represents a register in CPU, a general purpose register in CPU. So first, and the counter is a variable in main memory. So first, we have to load the variable into the register, and then the register incremented by 1, and then store the content of the register to the variable counter in main memory. So we use these at least 3 machine instructions to implement this high-level language statement. Okay. Also, as for counter minus minus, here in consumer process, counter minus minus, we also has to implement it used by these 3 machine level language. Of course, because we do not refer to any concrete CPU, so we just use pseudocode to represent machine instructions. So we use 3 machine instructions to implement counter minus minus, this high-level language statement. If both the producer and the consumer attempt to update the buffer concurrently, the assembly language statements may get interleaved. So, assuming that counter is initially equals to 5, one interleaving of statement is like this. In producer process, we use load instruction to get the content of the counter variable from main memory and put it into register 1. Then we incremented the register 1. Okay, so register 1 equals to 6, and the counter equals to 5 at the present time. And if the time slice, if if the timer interrupted, that means the time slice elapsed, then consumer is dispatched the CPU. So we can see the counter now equals to 5. So register 2 equal to 5. Then register 2 is decremented by 1. So register 2 equal to 4. Then the producer, register 1 equal to 6. So counter now by list store instruction, counter equals to 6. And by list store instruction in consumer precise, counter equals to 4. Of course, whether counter equals to 6 or equals to 4 depends which instruction execute at last. Finally, which instruction, these two instructions, which one executed finally, okay? So no matter counter equals to 6 or equals to 4, we know that the correct value is 5. So the value of counter will be either 4 or 6, while the correct result should be 5. We arrive at this incorrect state because we allow both processes to manipulate the variable counter concurrently, because we allow producer and consumer process to assign counter interleaved. Okay, actually, just now we say that these two statements must be performed atomically. What that means? Atomic operation means an operation that completes in its entirely without interruption. That means if producer execute counter plus this statement, then the system will not allow the consumer execute counter minus till the producer finish this statement. Then the consumer can assign the variable, the shared variable counter. Okay, so we have 2. So we have to do something. The operating system have to do something to ensure the data consistency. This circumstance here, counter equals to 6 and the counter equals to 4, we say data inconsistency. And the operating system has to do something to ensure data consistency. So let's look at it. So first let's know some concept or term, race condition. What is race condition? The situation where several processes assign and manipulate shared data concurrently. The final value of the shared data depends upon which process finishes last. So just like here, this example, we say it's race condition, okay? And to prevent race conditions, concurrent processes must be synchronized and coordinated.